Okay, so we're going to start off this electrochemical cells recap by thinking about electrolysis. Now, the difference between electrolysis and electrochemical cells is that electrolysis, you are supplying electricity in order to break a substance down, whereas in an electrochemical cell, you're using this cell in order to generate electricity. So instead of there being a power source in electrolysis for an electrochemical cell, the electricity would be going off somewhere. So when we look at electrolysis, this is our electrolyte, and our electrolytes are ionic compounds, and therefore they must be either molten or aqueous, as this means that our ions become free to move. We have two electrodes, so we have a positive and a negative electrode. So some people like to use the analogy of panic. So positive anode, negative is cathode. So here we've got our cathode and our anode. Now our anode is going to be attracting anions, which are therefore negative ions, and our cathode attracts cations, which are positive ions. Our electrodes are inert, so that they don't react with our electrolyte. However, sometimes we find that actually they react with the products that are formed at the electrode. For example, when oxygen is formed, that oxygen reacts with graphite electrodes in order to produce carbon dioxide, and so we have to replace those quite frequently. In terms of what's happening at our electrodes, then we need to think about something called redox. Now, redox is two words, two processes combined. So we have reduction and we have oxidation, and they are happening simultaneously, as whilst one species is being reduced, the other species is being oxidized. Now we have two definitions for each of these. So in terms of electrons, we often use oil rig. So therefore our oxidation is loss and reduction is gain. So again, this is in terms of electrons. In terms of oxygen, oxidation, we are gaining oxygen, and reduction, we are losing oxygen. In electrolysis, we're splitting up our ionic compounds. So our negative ion in the compound is attracted to the anode, and our positive ion in the compound is attracted to the cathode. And at the electrodes, they're going to either gain or lose electrons in order to form their element. So at our anode, our negative ions, in order to form its element, is going to have to lose electrons in order to lose that charge. And so because we're losing electrons, this is an oxidation, whereas at our cathode, are positive ions in order to form their element. In order to lose that positive charge, we're going to have to gain electrons in order to become neutral. And so because we're gaining electrons, then it's a reduction reaction. There are various uses of electrolysis. Most commonly we can think about it in our extraction of metals, but we have to be careful here in terms of our reactivity series as to whether we can use our molten or aqueous, because at our cathode our least reactive is formed. And so if we think about our reactivity series, so our most reactive being potassium, then sodium, then calcium, then magnesium, then aluminium, and then we have hydrogen. Now, whilst hydrogen isn't a metal, this is less reactive than these metals. And so if we're in solution, our water will also split up into H plus and OH minus. And so our H plus ions are also attracted to the cathode. And it's because of this that if we wanted to extract any of these using electrolysis, we would need to ensure that it's molten. However, it is through electrolysis that we use to extract these metals, and so the compounds must be molten so that we get our metal formed and not hydrogen gas. Another use of electrolysis is in electroplating, such as of coins. So you could have a coin as your negative anode, and then you would have the metal which would then coat that coin as your metal ions are attracted to your negative. At AS level we introduced some new terms, an oxidizing agent and a reducing agent. And what these are enabling oxidation to happen, and they are enabling reduction to happen. So the other species gets oxidized, the other species gets reduced, but as we said at the start, they're happening simultaneously. So whilst one thing is oxidized, the other thing is reduced. So for them to enable something else to be oxidized, they themselves are reduced. And our reducing agents are oxidized. So we can talk about our oxidizing agent is reduced as they gain electrons to oxidize other species, whereas our reducing reagent loses electrons to reduce the other species. We can look at oxidation states in order to tell whether something has been oxidized or reduced, and an oxidation state is telling us the number of electrons that have been lost or gained compared to an atom of the element. So number of electrons lost, in which case it's positive, or gained, in which case it's negative, compared to an atom of an element. And so then we can think about a number scale with 0 in the middle. So going up the scale, you're going from being negative towards being neutral, and so you are oxidizing. And again, if you were going from being neutral to positive, you'd have to be losing electrons, and so again oxidizing. Whereas going from positive towards neutral, you're having to gain electrons, and so we've got reduction happening. And then again, to become more negative, you're having to gain those negative electrons, and so it's reduction again. We looked last week at oxidation states and how we work them out for different compounds as part of our DIRT or AS revision activity. But we can also use this in order to balance equations by considering the two half equations that are occurring in a reaction. So, for example, we could have a reaction between our silver nitrate and copper. Now, as copper is more reactive than silver, it displaces the silver from the reaction in order to form copper nitrate plus silver. Now, we can balance this equation by thinking about our numbers of atoms of each type of element, but we can also consider what's happening in our half equations, what's happening to our transfer of electrons. Now, the first thing to note is that our NO3, so I should have included state symbols, these are both aqueous and solid copper and solid silver. So these are what's called spectator ions. So a spectator ion is one which doesn't change in a reaction. So this stays as NO3 minus in aqueous solution, both as a reaction and as a product. So it doesn't change during a reaction. Whereas our silver has gone from being Ag plus in aqueous solution to Ag solid, and our copper has gone from being a solid to Cu2 plus in aqueous solution. So what's happened in each of these cases? Well, in order to go from plus to neutral, we must have gained electrons. One electron is gained because it's a +1 to -1 in order to get to 0. And our Cu must have lost 2 electrons in order to go from copper to copper 2 plus in order for it to be oxidized. So then, in order for this reaction to happen, our number of electrons on each side of the equation must be the same. So if we label these equations 1 and 2, we know therefore that we're going to need 2 lots of that equation 1 in order for our electrons to be the same on our left hand side and right hand side when we add our equations together to give us an overall ionic equation, so one without the spectator ions. So 2 lots of 1 is a 2Ag plus 2E minus goes to 2Ag, and we're then going to add that to R2, so we're going to be adding Cu as a solid and adding Cu2 plus aqueous plus 2E minus. Now our electrons, because they're the same on either side, cancel, which is why we needed them to be the same on each side. And so then overall our ionic equation is 2Ag plus Cu solid goes to 2Ag solid plus Cu2 plus aqueous. And in order to then balance that original equation, we then just need to match up our stoichiometric coefficients. So 2 here means 2 there, and 2 here means 2 there. And now you should be able to see that our numbers of atoms on each side are the same. Do you remember that when a species is oxidized or reduced, and one of its oxidation states is where it is as an oxide, for example sulfur dioxide, instead of it being sulfur, we have to introduce water and acid in order to account for the oxygen atoms that have come as a result of that change in oxidation state. So remember to look at H plus and H2O when oxygen is present in an oxidized species.